All right, let's take a look at some nth roots. We can gain a lot of understanding about nth roots by thinking about what we do with square roots. We know that the square root of a is equal to b if and only if b squared is a. What we mean by that is that we know that the square root of 16 is 4 because 4 squared is 16. Okay. So when we look at nth roots, the nth root of a is going to equal b if and only if b to the nth power is equal to a. Now, something like the fourth root of 81, that's going to equal 3 because 3 to the fourth power is equal to 81. Lots of times we feel more comfortable with square roots just because we know perfect squares a lot better. When it comes to third roots, we know a handful of them off the top of our head. We know that 2 cubed is 8 and 3 cubed is 27. But beyond that, it takes a little guess and test and some just trying things out. One other thing that I want to point out is just some terminology when it comes to the fourth root of 81. Of course, the root here, that's called the radical. But the two numbers that are involved with the fourth root of 81 is dealing with this 4. Since it's a fourth root, that's called the index of the root. And this 81, the number underneath the root, has a special name as well. It's called the radicand. Let's simplify a handful of roots. If we're dealing with the square root of 16 y to the fourth, one thing that we can do, since 16 and y to the fourth are being multiplied together, is to break this up into the square root of 16 times the square root of y to the fourth. Now we all know that the square root of 16 is 4, but how about when it comes to the square root of y to the fourth? Remember the definition, it has to deal with finding perfect squares. So we want to rewrite y to the fourth as something squared. Well, that would be y squared, because when we take a power to a power, we multiply them together. Then, in essence, the square root and the square cancel with each other, and we're left with 4y squared. What I said about we gain a lot of understanding of higher power roots, thinking about square roots, is we can use that example to help us when it comes to the fifth root of 243, a to the 20th, b to the 25th. So just like how we split up that square root, we can split up that fifth root into the fifth root of 243 times the fifth root of a to the 20th times the fifth root of b to the 25th. Now, finding the fifth root of 243 might take some guessing and testing, or if you know where the fifth root button is on your calculator, you can use that. But the fifth root of 243 is 3. Then when it comes to these variables, if I want to find the fifth root of something, I need to write it in terms of a fifth power. So when it comes to a to the 20th, remembering that power to a power means we multiply, well, I would have to multiply 4 times 5 to make that 20. And for the fifth root of 25, that would be b to the fifth, because 5 times 5 would make the 25 that I need. So this will simplify to 3, a to the fourth, fifth root and fifth power cancel, so we'll have b to the fifth. If we're going to simplify the square root of x squared minus 6 to the 8th power, don't get hung up on that minus that's in the middle. If we're looking for a square root, I need to write this thing in terms of being squared. Well, we had x squared minus 6 to the 8th, and I want to raise that now to a power that I will then square. Well, 4 times 2 makes 8, so we'll take that to the fourth power. Then the square root essentially cancels with the square, and we're left with x squared minus 6 to the fourth power. Now, the most common mistake that I see happens with a problem like x squared plus 25 being the radicand of a square root. What you want to do is to say, oh, well, I know that I can take the square root of x squared, and I can take the square root of 25, and that means we're left with x plus 5. However, there's some flaw to that logic because the definition of square root said the square root of a is equal to b if and only if b squared is equal to a. That would mean that if I were to take this x plus 5 and square it, it should be equal to x squared plus 25, which we know it's not, because you would have to take x plus 5 times itself, and if we FOIL this out, we get x squared plus 10x plus 25. And we have this extra 10x in our square that is not in our radicand. Right? The idea is that we cannot distribute a square root over addition. If we look back at my other examples, they are all multiplication problems. So here's a big word problem that came out of the book as one of the examples in this section. But number of accidents between bicycles and vehicles is increased as the number of bikes at an intersection is increased. The relationship is modeled by the equation. Oh, look, a nice little equation right here. C is equal to the fifth root of b squared, where b is the number of bikes per week and c is the number of collisions at the intersection. How many collisions can be expected if the intersection has 1,000 bikes per week? Well, obviously this 1,000, since it's bikes per week, is going to be the b that we put into our equation. So c is equal to the fifth root of 1,000 squared. So you're going to have to take the fifth root of 1,000 squared. So there's 1,000. When we square it, we tack on 3 more zeros. So we're really talking about the fifth root of 1,000,000. If I were you, I would definitely break out that calculator, find out where your fifth root button is, and take the fifth root of 1,000,000, and we'll come with 15.848. And that would be collisions or accidents. You also might be asked something like this, where if we knew how many accidents there were, how many bikes passed through the intersection then? So if the number of accidents is 21, that is our C that we're going to plug into our formula. So we have 21 is equal to the fifth root of b squared. And now we have to start solving this equation. We can't just calculate it. So we think about, how do we undo a root? Well, when it was square roots, we undid a square root by squaring. This is a fifth root, so I'm going to take it to the fifth power. And I have to do the same thing on both sides. Now, when I take 21 to the fifth power, I get a really large number. 4,084,101. On the right side, though, the fifth root and the fifth power have canceled, and I'm left with b squared. To get rid of a square, I have to take the square root. The square and the square root will cancel. And when I take the square root of that 4,000,000 number on my calculator, I get 2,020.915. So that's how many bikes will pass through the intersection per week. 2,020 bikes per week.